Okay, the last steps for solving the PDE involving the Fourier series solution. Okay, so PDE always come along with boundary value problem. Therefore, the unknown coefficients obtained must be determined by using the Fourier series. Okay, we will determine it with the initial and boundary conditions given. This subsequently solve the PDE completely. So before this, we just solve the separable equation. So we try to see this step 3 from this example. Find the time dependent solution for uxt. Okay, now you have a function of x and t. Okay, when del u over del t equal to 4 del square u or del square u over del t square. Sorry, del square u over del x square, subject to, okay, BC is boundary condition and IC is initial condition. So for boundary condition, we substitute the value of x. For this one, you have x equal to 0, and this one you have x equal to 1. Okay, so initial condition, we substitute the value of t. Okay, t equal to 0, so your u is equal to 2x. Okay, so let's see this, how we solve this example. We will start with the first step. Okay, first steps. So in this case, we have 4 del square u over del x square equal to del u over del t. So we have del square u over del x square equal to 1 over 4 del u over del t. If you notice, this example is just similar to the previous example, but we have extra boundary condition and initial condition. Okay, so we just solved this before. We have see how we solve for the first step and second step before. So for the first steps, we have this one, and then we try to substitute. We let this case we have uxt equal to x multiplied by t. So we have x double prime t equal to 1 over 4 x t prime. So we divide by x t. We have x double prime over x equal to 1 over 4 t prime over t. Okay, so x double prime over x is equal to k, and then we have 1 over 4 t prime over t equal to k. For this one, we have x double prime equal to kx. We move the x, and then we have x double prime minus kx equal to 0. For this one, we have t prime equal to 4 kt. Okay, we move this 1 over 4 and t, and then we have t prime minus 4 kt equal to 0. So we have these two ODE, and then for the second steps, okay, for second steps, we consider the first case when k is positive. K positive, we let k equal to lambda square. So substitute x double prime minus lambda square x equal to 0. Okay, next find the roots. So m square minus lambda square equal to 0. So m is equal to plus minus lambda. You have two roots here. One you have positive lambda, second one you have negative lambda. So for x, you have c1 exponent lambda x plus c2 exponent minus lambda x. Okay, we will solve the equation of x first, because this equation comes with boundary condition. These boundary conditions. So the boundary condition will allow us to narrow down the possible solution. Okay, so just focus on the x first instead of t. Okay, so now you just have x. So we substitute is the boundary condition. So the first boundary condition state that when x equal to 0, then your x is equal to 0. Okay, when x 0, so this is equal to 0. And then when you substitute x equal to 0, you have c1 exponent 0 plus 0 lambda plus c2 exponent minus 0 lambda. This is equal to 0. Substitute x equal to 0, you have 0. So this one, c1 multiplied by 1, you have c1, c2 plus c2 multiplied by 1. So you have c1 plus c2 equal to 0. Okay, and the second step, the second boundary condition, del u over del x. Substitute x equal to 1, you have 0. Meaning that you need to find the x prime. Okay, in order to use the second boundary condition. Okay, so now you have x here. Then find x prime. X prime x is equal to, for this one you have lambda c1 exponent lambda x plus minus lambda c2 exponent minus lambda x. So this is equal to lambda c1 exponent lambda x minus lambda c2 exponent minus lambda x. So you have your x prime. So here the boundary condition, the second boundary condition state that your x prime is equal to 0 if your x is equal to 1. So substitute the value. You have lambda c1 exponent lambda minus lambda c2 exponent minus lambda. This is equal to 0. So you have lambda exponent lambda, so yes, multiplied by c1 minus c2. This is equal to 0. This is how you factorize this. You have lambda exponent lambda, so you just have c1 minus c2. Okay, so we have two equations here for c1 and c2. First we have c1 plus c2 equal to 0. So for this one we have c1 equal to minus c2. And another one here we have c1 minus c2 equal to 0, which means c1 is equal to c2. So from these two examples we can conclude that our c1 is equal to c2 is equal to 0. Okay, so for this one we conclude that there is no eigenvalue since our c1 and c2 is equal to 0. So there is no eigenvalues in this case. For this case, for k is positive. Thus, we omit this case. We cannot solve for this case. Since we cannot solve for the first case, we move to the second case. We try to solve for the second case where our k is equal to 0. Okay, let's see if we can have our eigenvalues for second case. Okay, for the second case, x double prime minus 0x equal to 0, and then we have t prime minus 4kt where k is 0, so we have this is equal to 0. Characteristic equation, m square equal to 0 and this is m equal to 0. So our x here is equal to, we stop at c2 here, so we continue with c3. So we have c3, So M1 equal to M2 equal to 0. So C3 exponent 0x plus C4x exponent 0x. Why? Because the roots is real and repeated. So we have C4x here. So x is C3 plus C4x for x. Again, substitute the boundary condition for x first. Okay, the boundary condition. So you need to find x prime. Substitute. When x equal to 0, when x equal to 0, x is equal to 0. So x 0 is equal to 0. Then you have C3 plus C4 multiplied by 0 is equal to 0. So you have C3 equal to 0 for the first boundary condition. For the second boundary condition, find the x prime. X equal to, so this one, differentiate this, you have C3, 0, 0 C3, and then you have C4. Okay, so for second boundary condition, x prime, x equal to 1 is equal to 0. So x prime 1 equal to 0. So for this one, x prime C4 equal to 0. Again, you have C3 and C4. Since C3 equal to C4 equal to 0, so there is no eigenvalue. Okay, there is no eigenvalue for second case where k equal to 0. We omit the case. Okay, so but we still have the third case. So now we proceed with the third case if we can find the eigenvalue. The third case when k is negative, lambda square. So x double prime plus lambda square x equal to 0 and t prime plus 4 lambda square t equal to 0. Okay. Characteristic equation for this, m square plus lambda square equal to 0. So m square equal to minus lambda square. Okay, when you apply the square root, so you have m square root of minus 1. So this is I, imaginary part of complex number. So square root of lambda square will be plus minus lambda. Okay, so complex conjugate your x become, since a is 0, so you just have c5. We stop here at c4, so we continue with c5. c5 cos lambda x plus c6 sin lambda x. Substitute the first boundary condition, x 0 equal to 0. Then you have c5 cos 0 plus c6 sin 0 equal to 0. Sin 0 is equal to 0. Cos 0 is equal to 1. So you have c5 equal to 0. And then we have the second boundary condition, x prime 1 equal to 0. So find the x prime for this one. So your x is equal to c5 cos lambda x plus c6 sin lambda x. So x prime for this is differentiate cos, we have minus c5 lambda sin lambda x plus we have c6 lambda cos lambda x. Okay, so x prime. So the second boundary condition, x prime 1 is equal to 0. So for this one, substitute x equal to 1. So you have minus c5 lambda sine lambda plus C6 lambda cos lambda equal to 0. Okay, substitute x with 1, you have this whole expression equal to 0. Okay, so for this one, since the C5 is equal to 0, so substitute the C5 equal to 0 here. You have 0 plus C6 lambda cos lambda equal to 0. Okay, so you have C6 lambda cos lambda equal to 0, and you need to make sure that C6 cannot be equal to 0. Why? Because you already have C5 equal to 0. If the C6 is equal to 0 as well, so again you don't have any eigenvalues. So there is no use to do all these three cases. Okay, so make sure, the first thing you need to do is to make sure that C6 is not equal to 0. So since C6 cannot be equal to 0, so lambda cos lambda should be equal to 0. So for this one, we just focus on cos lambda equal to 0. Okay, what is the value for lambda that made this cos lambda equal to 0? You will find that lambda is pi over 2. Okay, 3 pi over 2. Because when you try to find the cos pi over 2, cos 3 pi over 2, cos 5 pi over 2 up to n pi over 2, this will give you the value of 0. So lambda is equal to this value. Okay, so basically if you want to generalize the lambda, this will be 2n minus 1, because this is odd number, 1, 3, 5, 7, okay, over 2 pi. Then n can be equal to 1, 2, 3. Okay, if you substitute n equal to 1, you have 1. Substitute n equal to 2, you have 3 pi over 2. So we have generalized our lambda n, our eigenvalues. So our eigen function, which is our xn, will be, substitute the value. Okay, our x for the third case is xx equal to c5 cos lambda x plus c6 sin lambda x. So substitute your value. You have your c5, your c6, and then you have your lambda. So substitute into this. So c5 is equal to 0. So we don't have this term because c5 is 0. 0 multiplied by cos, we have 0. So we just have c6 here. So c6 will be cn, because we want to write this xn in general form. We use xn instead of x. Here we use xn in general. So c6 will be cn sin lambda. So now we have lambda n. For the we have general lambda. So we use lambda n x. So our lambda n now is, so this is sin 2n minus 1 over 2 pi. Okay, 2 pi, and then we have x here. Okay, so this is for xn. Go to our t. Okay, t prime plus 4 lambda square t equal to 0. So m plus 4 lambda square equal to 0. So our m is minus 4 lambda square. So t is equal to c. What do we have now? We stop at c6. So we have c7 here. C7 exponent minus 4 lambda square t. We have t equal to c7 exponent minus 4 lambda square t. So write your general t. T and t is equal to instead of C7, okay, we use, let's say, Bn or Dn. Okay, we have xn, we use Cn. So this one, let's say we use Dn. So exponent minus 4, and then this is lambda n square t. Okay, we want to write this t in general. So this is Dn exponent minus 4. Our lambda n is equal to this. So substitute the value for lambda n. We have 2n minus 1 over 2 square t. Okay, so this becomes Dn 2 square is 4, so it can be cancelled. So exponent minus 2n minus 1 square t. So we have xn and tn. So now we can write our u x t equal to xn multiplied by tn. This is equal to cn sine 2n minus 1 over 2 pi x multiplied by dn exponent minus 2n minus 1 square t. Okay. So we simplify this. Okay, cn multiply dn we can write as bn. So we have bn exponent minus 2n minus 1 square t sine 2n minus 1 over 2 pi x, where our bn is a product of cn and dn. Since this is just a constant, so we can write this product of constant with another constant, bn. Okay, so bn is equal to, so we have our un equal to this function. Okay, sorry, we have lambda and here we missed the, I missed the pi here. So we have pi square. When I substitute the lambda n, I miss this pi. Where is it? This one. Yes, I missed this pi. So we have extra pi square here, and then I have pi square here. So this is pi square. Okay, so from un xt, we can write this as summation. So u xt is equal to summation n from 1 to infinity bn exponent minus 2n minus 1 square pi square t. Okay, sine 2n minus 1 over 2 pi x. We don't have, so from un we have u, but we write the summation here. So now you see this is more looks like Fourier series. Okay, so we can substitute our initial condition. The initial condition when t equal to 0, u is equal to 2x. Okay, substitute t equal to 0, we have our u equal to 2x. So this one, substitute t equal to 0, our u equal to 2x. So this one is equal to summation n equal to 1 to infinity bn. Substitute t, sorry, bn, substitute t equal to 0. So the whole things here will be exponent 0. So exponent 0 is equal to 1. Okay, so c sine 2n minus 1 over 2 pi x. Okay, so we just have this one when we substitute the initial condition. Okay, we don't have this exponent because our t is 0, so exponent 0 is equal to 1. So now you see this one, we can solve for bn using the Fourier series. So bn is equal to 2 over L. Okay, 2 over L from 0 to L, our fx And then we have sine this one. Sine 2n minus 1 over 2 pi x dx. Okay, the question is what is L and fx? Okay, so this is your fx. Your initial condition is your fx, and your L is equal to this one. L from 0 to L equal to 1. Okay, so L is equal to 1. So from here you have 2 divided by 1, 0 to 1, and then your fx is 2x sine 2n minus 1 divided by 2 pi x dx. Okay, solve this using the tabular method. For tabular method, we have differentiation and integration. So this 2x will be on the differentiation side, and this sine 2n minus 1 on the integration side, pi x. Differentiate 2x, you have to differentiate again, you have 0. You have plus, minus, plus. Integrate sine, you have cos 2n minus 1 over 2 pi x. And then you have to divide this with differentiation of this one. So you have 2n minus 1 over 2, integration sign, you have minus cos over 2 pi. Okay, so let's solve this. So this is equal to 2 over 2n minus 1 pi minus cos 2n minus 1 over 2 pi x. Okay, and then we have 0 here, we have plus here, and then we need to do the integration for this one. Okay, the integration for this one is equal to, you integrate cos, you have, so you have minus 2 over 2n minus 1 pi, integrate cos, you have positive sine 2n minus 1 over 2 pi x divided by 2n minus 1 over 2 pi. So this is equal to minus 4 over 2n minus 1 square pi square sine 2n minus 1 over 2 pi x. So substitute here, you have 2, and then 2x multiplied by this term. Okay, so you have minus 4x over 2n minus 1 pi cos 2n minus 1 over 2 pi x. Okay, plus minus, and then you have minus 2 multiplied by this. Okay, minus 2 multiplied by this, you have plus 8. Okay, plus 8 over 2n minus 1 square pi sine 2n minus 1 over 2 pi x. So from 0 to 1. So you have 2 here, substitute 1, you have minus 4 over 2n minus 1 pi cos 2n minus 1 over 2 pi plus 8 over 2n minus 1 square pi sine 2n minus 1 over 2 pi. Okay, substitute x with 1. So minus plus 0, because 4 multiplied by 0 is equal to 0. And then you have minus 8 over 2n minus 1 square pi sine 2n minus 1 over 2 pi 0. This is 0. Okay. So you have cos this value and then sine this, and then you have sine 0. Sine 0 is equal to 0. Okay, so we have Bn is equal to this. Okay, so since this is equal to 0, so we just need to consider this 2. Okay, so there is a helpful tips here. So you need to note that sine 2n minus 1 over 2, this one is equal to minus 1 to the power of n plus 1. So this is equal to minus 1 to the power of n plus 1, while the cos 2n minus 1 over 2 pi, this one is equal to 0. Okay, so this is the extra tips. Okay, so our Bn now is equal to 8 over 2n plus 1 square pi. Yes, this is pi square, this is pi square. Okay, pi square sine, substitute sine value minus 1 to the power of n plus 1. Okay, so this is equal to 16 minus 1 to the power of n plus 1 over 2n minus 1 to square pi square. So our Bn is equal to this. This is our UXT. So write back your UXT. This is your final answer. Your UXT is equal to summation n equal to 1 to infinity. Then substitute your Bn, 16 minus 1 to the power of n plus 1 over 2n minus 1 square pi square. Okay, so this is exponent minus 2n minus 1 square pi square t sine 2n minus 1 over 2 pi x. Okay, so this is the last answer. Okay, so let's conclude how we solve the PDE. Okay, so this method is a very long method. I mean, to solve for PDE, you have a very long work. Okay, for example, you start with first steps, and then for the second step, you need to consider the 3 cases. Okay, but end up you just need to focus for the third case, because case 1 and case 2 normally will give you no eigenvalues, and then you have to omit the case. So basically we will find the answer in case 3. So the tips is, normally for the final examination question, the instruction will ask you to just keep the first 2 case, omit the 2 first case, and then just start with the third case. That's normally how the question for final exam. But if in your final they ask you to prove that the first and second case has no eigenvalue, so you need to start with the first and the third case. If not, you just start with the third case where k is equal to negative value. Okay, so still it have a very long works to do. Okay, so you start with case 3, and then you have your x, and then you need to substitute the boundary condition, you need to find the C6, and then you need to do you need to solve for the Fourier series. For this example, you just have this Bn. For some cases, you might have to find the A0, AN and BN. Okay, so for this one you just need to find the BN, but it's still confusing. So be careful and do a lot of exercise on Fourier series. That will help you to solve for PDE as well. Okay.